Hi, everyone, and welcome to IPDLN 2020. Thank you for joining us at the Advanced Analytics AI and Machine Learning session. My name is Michael Folster. I'm a Senior Research Fellow from the Centre for Big Data Research in Health in UNSW Sydney, and I'll be your session chair for this session. Today in this session, there's going to be 4 10-minute presentations followed by 20 minutes of questions and discussion. If you have any questions for any of the speakers, please feel free to use the Q&A function down on the right-hand side of the screen to ask any questions. You can enter these questions at any time during the presentation. So if you have any, please feel free to enter them. And if you see another question that's of interest, please feel free to upvote that to make sure that I can get to that question at the end. Now, without any further ado, let's get started. Our first speaker is Branson Chen, who's a health information analyst from ICES Canada. And Branson will be talking to us today about deep learning and natural language processing for knowledge extraction from laboratory reports. Thank you very much, Branson. So,
hi, everyone.
Great.
So, can you hear me? Okay, great. Hi, everyone. Thank you for attending this talk on deep learning and natural language processing for knowledge extraction from laboratory reports. My name is Branson Chen. I work as a senior health information analyst at ICES, where I'm involved in multiple health research projects that leverage free text data from electronic health and medical records. This project was formed as a collaborative effort between ICES and Vector Institute. ICES is a health research organization that stores health services records for approximately 15 million people in Ontario, which is Canada's most populous province. We also have over 200 scientists that have expertise in many areas of health research. Vector Institute is an artificial intelligence research organization that has many deep learning and machine learning experts. They work with many partners to advance AI research and drive its application across Canada. Both are independent, not-for-profit organizations that are committed to producing robust, high-impact research that improves the lives of Canadians. As such, it was very natural for our organizations to work together and to use AI to advance health research. One common problem when working with electronic health records, or EHRs, is the complexity of the data. The largest data holding at ICES is a copy of the Ontario Laboratories Information System, also known as OLIS, which we received from Ontario Health. This repository covers most hospitals, community labs, and public health labs across the province. It's known that reuse of EHRs can reduce costs and inefficiencies associated with clinical research, but unfortunately, the data are often not recorded as accurately as research data. And thus, a lot of pre-processing is required before EHRs become a truly valuable commodity. And natural language processing can help with these types of information extraction tasks. I'll just give a few quick examples of what NLP models can do. There's entity extraction, which identifies and classifies key elements or terms to make the text data available for more standard processing. Entity linking assigns a unique identity to entities, such as famous locations or famous individuals. Entity resolution finds overlapping references to real-world things in the data. And lastly, topic modeling can automatically identify topics that are present in the data. Now that we know what kinds of things NLP can do, let's look at what it can be applied to. So OLIS, the laboratory information system, has over 5 billion laboratory observations coming in 2 main forms that require different methods of pre-processing. For structured numeric values, we apply cutoff points to remove outliers and noise, and sometimes scale values as well. For unstructured text, we need to manually review records and interpret the text information within. We often use rules-based string matching and regular expressions to parse the relevant information out. And all of these data cleaning tasks require the input of various clinical content experts. These pre-processing tasks are very costly and time-consuming, especially for unstructured data. One area of interest among laboratory reports that contain free text at ICS is common respiratory viruses. Our goal was to develop an NLP tool to designed to, one, extract entities. These would be respiratory virus test results, and two, encode this information into a usable format for researchers. Ultimately, this would save on time and costs for extracting respiratory virus-related data for downstream epidemiology studies. We looked at respiratory virus lab reports from 2007 to 2018 in OLIS, which contained around 1.3 million free text observations. This dataset had observations under 100 different links. This is a universal coding system for identifying medical lab observations. And the clinical text was cleaned, tokenized, and parsed using an in-house text algorithm that I developed that did not use any NLP models. So this is before the NLP work. And this algorithm was iteratively refined with manual review from multiple clinical experts. This data was then encoded as virus, result, and test types to be used as a ground truth. Another output of the algorithm was labels corresponding to whether each token or word was a key element or not, as you can see in this example. This information was then fed into our NLP model for classification training. Our NLP tool is a modular system of pipelined components, including a named entity recognition module for extracting mentions of virus, result, and test types to eventually combine into a meaningful outcome. Specifically, we used a recurrent neural network model called bidirectional long short-term memory, or BiLSTM, to train the classifier. Here's an example of the classification, which picks out key elements from a string. We are currently in the process of evaluating the classifications and working on the second part of the project, which is to encode the extracted entities into a research-ready form. Eventually, in deployment, the NLP model could be applied directly to incoming OLIS data, but we would still require some manual review to make sure that it is working as intended. The NLP tool was built on ground truth data produced by our in-house algorithm that was mentioned beforehand, and based on our test set, it achieved an accuracy greater than 95% for entity extraction. This here is just a visualization of how the model sees the sequences of tokens. On the left are the vector representations for words in our corpus generated using GLOVE, which is a publicly available model for obtaining vector representations trained on public data. This is without any of our modifications on the left-hand side. We fed these vector representations into our NLP model, which uses supervised learning and changes the representations of the words for classification. On the right, we see the output showing clustering of certain terms, meaning that they have a similar context. So you can see some result words are clustered together, some negative words, certain types of viruses are clustered together, and certain viruses are clustered together too, depending on how the words get interpreted by the model. In conclusion, our NLP tool, once finalized and validated, could be reusable for data sets with similar information, and we hope that it will be deployed into clinical systems to provide on-the-spot analysis of various lab reports. It was cost-effective to create, but the training requires high-performance computation power. And it also requires accurate annotations for the training process and for maintenance of the tool over time. For next steps, since ICES receives updates to OLIS regularly, we plan to test the model on more recent data, which can include new information such as COVID-19 data. We are also working on encoding the extracted entities into a research-ready form and figuring out how to best deploy this tool. I'd like to thank our team, Jeff, Mahmoud, Hannah, and particularly Elham, the technical AI scientist who worked on all of the NLP models. And thank you all for listening.
Thank you very much, Branson. That was a really interesting talk. A reminder to everyone, if you have any questions, please enter them in the Q&A section on the portal, and we will discuss them all at the end of the session. And I'll just also let you know we've had a slight shuffling of the order of presenters today due to some technical issues in the back. And so Liisa, who was originally scheduled to present first, will now be the fourth panelist who will be chatting with later. So now we'll move on to the second speaker, Mahmoud Azimaee, who is the Director of Data Quality and Information Management at ICES Canada. And Mahmoud will be talking about MASK, a success story for an international collaboration. Thank you very much, Mahmoud.
Thank you for the introduction, Michael. Let me share my screen. All right. Good evening, good morning, or good afternoon, wherever you are in the globe. And as Michael said, I'm a director as a data quality and information management at ICES. You heard about my house institution. It's from Branson in the previous presentation. We are a not-for-profit research institute funded mainly by the government of Ontario. We are located in Ontario, Toronto, Canada, and we are connected to 6 sites, satellite sites at the universities across the province. We hold over 100 linkable Ontario population level health and non-health data. That's contained 24 billion records of basically individual level data, over 500,000 data fields, and some of these data are being updated on a daily or monthly or quarterly up to annual updates. Currently, we have 263 scientists and 280 staff, and last year we had 678 peer-reviewed publications. Free text medical narratives. You heard a little bit about this when Branson was giving a talk about lab data at ICES. As you know, a significant amount of valuable information in EHR and EMR are embedded in lengthy free text data. Examples are lab data, echocardiogram, interpretation, and progress note, for example, in EMR. This is an example of our COVID-19 test results in Ontario. This is a real example, of course, de-identified. You can see that being a positive or negative test is embedded in a very long paragraph, and this is just part of it. The challenges that comes with the free text field obviously is personal information. Often patient information or personal informations are included in these narratives. And as you know, privacy legislation requires to de-identify this information prior to making them available for research. This is another example of one of our lab test results for C. diff. As you see, other than the result that is being positive, you can see information that the information was phoned to this number, which is probably a local public health number. And also it says who performed the test. This is another example from an echocardiogram interpretation that in addition to the interpretation of the echocardiogram, it also said that, by the way, patient name was something else, and there was a misspelled in the data. So you can see the actual patient name as a comment in the interpretation of the echocardiogram. So to address these issues, a while ago, many years ago, we came up with this rule-based and dictionary-based tools. We called it MASK. It was developed in-house at ICES using per regular expressions in SAS. And as you see this in this screenshot, we highly relied on the methodology that was given in these BMC papers by Ishna Nimatullah and others. And we actually adapted and advanced it more for ICES and Ontario data. It worked, but we faced with new challenges, of course. Some of you may recall this YouTube video. If you were in 2018 IPDLN Conference, at that conference, I was voluntold to make a video for Science Slam section for the conference. And I'm not going to play this video. It's long and we don't have time for it, but you can easily find it on YouTube if you search Master Parkinson or Parkinson the disease. So I tried to, in a funny format, to present it, but what is the challenge and what we have done until 2018 and what we were planning to do. And now it's a good opportunity for me to tell you what happened after 2 years from Calgary's talk and conference back in 2018. In this screenshot, you can see a few examples. These are echocardiogram. So you can see, for example, Carpentier-Edwards valve, or Duke treadmill score, or St. Jude mechanical valve. So these are examples of names, individual names. Basically, these are devices that are named after individuals. And we happen to have all of these names in our patient registry. And if we rely on only rule-based and dictionary-based methods, we're going to mask all of this useful and important information. So it would be over-masking the results, and basically you're going to lose the value of the data that you were hoping to analyze. So what we did, we realized that we need a contextually driven methods, AI-based. We didn't have, unfortunately, the skill at ICS. So we teamed up with Manchester University, the Department of Computer Science, Professor Goran Anadik and his team of data scientists. We also collaborated with Eventset, a Toronto-based custom software company, to help us in this journey. And obviously, to start a collaboration, Zoom is not enough. It was pre-pandemic, so we traveled to Manchester to meet Manchester team. They traveled back about a year after to visit ICES, and we hosted a postdoc from Manchester at ICES in order to allow or give an opportunity to run the models that we were developing against real data. And please don't ask me why traveling from Toronto to Manchester is shorter than traveling from Manchester to Toronto, and even cheaper. So we know that Manchester University had a de-identification framework for name entity recognition. So we used that framework. And also we developed 3 machine learning based algorithm for name entity, CRF, GLOVE, and ELMO. These models were tested on publicly available data, as well on 3 different ICS databases, Lab, EMR, and ECHO. Eventset company developed the user interface and masking modules. And those modules can be tuned further on any local data, of course. But what we created as a basic package was the ones that were trained on publicly available data. So in this slide, you can see a few screenshots of the actual interface of the application. So when you run the application, it asks you, would you like to mask a document or a data, or do you want to actually train or adding a training model? And then it asks you what are the data elements or entities that you would like to mask in this data, and also what are the models for each of these entities that you would like to apply. I'm pleased to let you know that the whole package is licensed as open source under ICS GitHub repository. It's licensed under Apache version 2 open source license, and basically the entire basic models trained on public data, as well the interface is available for use. The next steps that we are planning for this project is to further labeling and training the models using ICS data. So we are annotating EMR, ECHO, and lab data to have a bigger data for training. And the plan is the models that will be trained using ICS data will be licensed differently in order to respect the Ontario's health data requirements. But obviously, any organization, any entity can go and download the basic models from GitHub and start training them based on their own data. This is the list of all individuals in this project from ICS, from Manchester, and from Eventset. I'm grateful for their collaboration. And that was all. I'll be happy to answer any question at the end of the session. Thank you. Michael, you are on mute.
Sorry, everyone. Thank you very much, Mahmoud, for a fantastic talk. I know people are dealing with similar issues in using data all around the world. I know we are in Australia, so that was a really, really interesting talk. Look, just for a second, I'll just ask if Liisa can pop on her microphone and say hi, just to see if we've resolved some tech issues.
I hope you can hear me.
We can, Liisa. Fantastic. That's great.
No stress. No stress.
The joys of an online conference, but thankfully this has worked out really well. So look, with that, I'll move on to our third speaker, Derrick Lopez, and we'll come back to you, Liisa, after that. Derrick is a research fellow at the University of Western Australia, and today Derrick will be talking about evaluating machine learning models for predicting hospital transfers and administrative data. And just a reminder, if you have any questions, make sure to enter them in the portal. Thank you, Derrick.
Thanks, Michael, for the introduction. Good morning, afternoon, or good night, evening, everyone, wherever you are. I am a health service researcher, and this was done in conjunction with my data scientist colleague, Joan Liu, who's one of the co-authors on this paper. So firstly, for the background of this presentation, myocardial infarction or heart attack is a major cause of mortality in Australia and in many countries. Accurate counts of MI admissions is essential for evaluating public health measures and health service utilization. These counts are based on administrative health data. However, in this data, each transfer is a separate record. If a patient has multiple transfers, this will result in multiple admissions for what is essentially a single MI event. Variables like admin from and discharge to in hospital data are not reliable as they were collected for administrative use rather than for research purposes. We have previously shown that if transfers are not considered, as in this graph here shown by the red line, and such as when using unlinked data, the number of MI events can be inflated. Furthermore, if we do not consider transfers, we can also underestimate case fatality due to a larger denominator. Current national estimates use unlinked data. And with this in mind, we sought to determine if we can identify transfers in hospital data using machine learning methods. So the rationale for this study is that there are other variables in hospital data apart from admin from and discharge to that can inform us if a record is actually a transfer-related admission. For example, a patient aged 45 years will be more likely to be transferred out for further care compared to an 85-year-old patient. Patients discharged alive at 2 a.m. in the morning or the discharge destination is another hospital, they are more likely to be transferred out as if someone that was admitted to rural or remote hospital. Similarly, someone admitted to a tertiary hospital is more likely to be transferred in. So the aims of our study were twofold. Firstly, to determine if logistic regression and machine learning approaches can predict transfers based on a range of variables available in hospital data. Secondly, to compare the number of MI events from machine learning approaches against our manual identification of transfers. For this study, we used linked Western Australian hospital morbidity data from 2000 to 2016 for all admissions for cardiovascular disease cohort we identified transfers using all records with a one-day window between subsequent discharge and admission, which I will show you in the next slide. Following this, we retain records relating to MI admissions only in the principal diagnosis field. We then pass this data through machine learning approaches to determine if we can predict transfers in each individual record based on variables in the data. Here is how we manually identify transfers. Records 2, 3, and 4 are transfers relating to patient 1. As you can see, there's a one-day window between the discharge and subsequent admission. Similarly, record 6 is a transfer for patient 2, and record 8 is the transfer for patient number 3. In this example, there are 8 MI records, but it only represents 3 MI events. So as I mentioned earlier, we can overestimate the burden of MI if we do not take transfers into consideration. For the purpose of this study, for analytical purposes, we transpose the transfer codes of 0 and 1 as shown, and we use non-transfer. Here are the variables from the data that we use. These variables, we feel, could inform us if a record is actually a transfer-related admission. Apart from logistic regression, we use random forest and gradient boosting machine. These approaches are based on decision trees. Random forest is based on multiple decision trees independently trained on a random subset of data. On the other hand, gradient boosting machine is based on sequential addition of decision trees. Each new iteration involves adding a new decision tree which learns from the residuals of the previous tree to improve its prediction. Here are parameter settings that we use. For logistic regression, we use all variables each time, whereas for random forest and gradient boosting machine, the random selection of variables was selected. The data set was split 75% for training and 25% for testing. So just a bit about the data we had. We had 75,000 MI records in the principal diagnosis field. Of this, 64,000 were for non-transfer records and 10,000 were for transfer records. There is a class imbalance with the split being 86% for non-transfer and 14% for transfer. As described earlier, we coded non-transfers as 1 and transfers as 0. To answer our first aim, we looked at the model performance of these 3 approaches. Of these 3 approaches, gradient boosting machine had the best sensitivity and area under the curve as shown by the red box, while random forest had the best specificity and positive predictive value. Logistic regression was the worst performer amongst these 3 approaches. Here are our probability curves. As I mentioned earlier, non-transfers were coded as 1 and transfers as 0. Ideally, the curves should look like the one in the top left corner, where non-transfers, which was coded as 1, should pick around 1, as shown by the red area, and transfers, which coded as 0, should pick around 0, which is shown in green. Logistic regression had the worst curve, as shown in the top right corner. Random forest and gradient boosting machine had good probability distribution curves for non-transfers, but poor distribution for transfers. And this is likely due to the class imbalance, where only 14% of the records were for transfers. To address our second aim, we use the calculated probabilities to determine the annual number of MI events using the test dataset. Any record with a probability of 0.6 or higher was defined as a non-transfer. The blue line represents the number of MI records without considering transfers. The black line is the number of events accounting for transfers using a manual identification of transfers. and the red line addresses transfers using gradient boosting machine. As you can see, gradient boosting machine produced similar results to a manual method of identifying transfers. And we had similar results for a random forest, which I will not show. On the other hand, logistic regression produced inferior results. There was an undercount of the number of MI events as shown as the red line here. So what are the implications of this study? So machine learning approaches like gradient boosting machine and random forest can predict transfers in individual records in hospital data with high precision. They can be used to determine a number of events or rates. It can be useful in unlinked data where records belonging to the same patient cannot be identified. There's a potential for this algorithm to be applied to other medical conditions where patients are frequently transferred. Our limitation was that the data was trained and tested on Western Australian data for MI admissions from 2000 to 2016. We have studies currently planned to determine if we can generalize these findings outside these conditions. Before I end this presentation, I would like to acknowledge the following for making this study possible. Thank you.
Thank you very much, Derrick, for that really fantastic talk. Just a reminder, if you have any questions, make sure you add them in the question Q&A panel on the right-hand side of the portal, and we'll get to those just after we wrap up with Liisa's talk. So that leads me to Liisa, who's our last speaker for the session. That's Liisa Jaakkimainen, who's a senior core scientist and program lead at the Primary Care and Health Systems program at ICES in Toronto. And also, an associate professor in the Department of Family and Community Medicine at the University of Toronto too. Liisa will be talking about using machine learning to measure specialist wait times from family physicians' electronic medical records. Thank you very much, Liisa.
Hi, can you actually hear me?
Yes.
And can you actually see my, where is it? Where's my talk? Can you see my talk?
Not yet.
Share?
Yeah. Oh, yeah.
Sorry, I'm having my son help me with this. It's his computer. What can I say? Okay. Okay, where is it?
Yeah. Oh. That I don't actually have screen sharing enabled, so I'll have to restart Zoom for a sec.
Oh, Oni, hold on.
Look, my apologies about that. I think we've all experienced issues with IT every now and then, and it's just what we're going to be working through. So look, Liisa, I see you're back on.
Yep. Let's see if we got this thing. Share here. And there.
Yep, share.
Do I have to click on it though?
No, just click share.
Share. Can you see it now?
Yes, we can.
Oh my goodness. And here we go. Ooh, I think.
All right.
Okay, my goodness. So my talk's about using machine learning to measure specialist wait times from family physician electronic medical records, which are linked to administrative data. Good, that worked. Just to let you know, this is it's a grant that's supported. It was supported by a grant, and I actually want to go back to the title page. So Mohammed Abdallah is actually used this work as part of his PhD in computer science at the University of Toronto, and he really should be recognized for this work. It is supported by a grant. We have no in-kind support, and there's no conflict of interest. I'm really interested in using determining wait time. So reliable information about time spent waiting for healthcare is a critical metric for measuring how well a health system is performing. And currently in Canada, we do this by linking existing health administrative data, or we use hospital inputted portal systems. The focus mostly has been from the wait time from seeing a specialist physician to having a procedure or a therapy. And we know that patients experience wait times far before they see a specialist physician. They have the wait to see a primary care doctor. In Canada, that would be a family doctor or nurse practitioner. There's the wait from the referral from primary care. And there's also the wait of getting information back to the primary care physician. And why we're interested in this is, unfortunately, in Canada, for several Commonwealth surveys, Canada is ranked 10th out of 11th Commonwealth nations on access and 11th out of 11 nations for the timeliness of healthcare. And in fact, in Canada, the Fraser Institute survey in 2019 found the wait time from family physician referral to seeing a specialist was 8 weeks, which was an increase from their previous survey. And while surveys are very important and provide a lot of information, they're expensive, they're time consuming, and they are prone to some recall bias. Increasingly in Canada, family physicians use electronic medical records for their care, and you've heard about this before with Mahmoud and with Branson. And more over the last 10 years, where did my talk go? Uh-oh, did you see my talk?
It's disappeared now.
And
your error screen about Adobe Flash.
Yeah. Okay, I'm not sure this is going to work. Remind me later. No, it's still not going to work. Owen, it disappeared. This is not working well for me today. Hold on, I'm just going to mute myself.
Well, I'll also note Liisa, we've had a comment from Liisa Sharwood saying, thank you for persisting, Liisa, and to your son, we have all been there. Indeed, we definitely have. So great, it's back on now, Liisa. You can unmute yourself.
Can you hear me now? There. So anyways, like I was saying, the EMR data that exists, it consists of very structured data like blood pressures and weights and heights, all the way to unstructured data, which is words. And there's a vast amount of information in EMR data that's in the Word format. Previously, we had done a study where we looked at wait times linking EMR data to health administrative data, and we had to hire an abstractor to go in and codify the referral notes, because they were all words with no destination for the referral note. So what we thought, it would be interesting to see if we could identify the target specialist physician from the EMR data using machine learning, and then link it to the administrative data to look at wait times. We used EMRPC, which has been described in previous talks, and we linked it to the physician claims data in Ontario. And EMRPC is a convenient sample of over 400 family physicians across Ontario from 46 clinics, over 500,000 patients. And these family physicians provide the entire, their entire EMR record to ICS for linkage and for research. So what we did was we conducted a record linkage study on a cohort of patients who had a referral made by their family physician in 2015. The usual criteria, they had to have a valid healthcare number, date of birth, and at least one referral made in 2015. And the family doctors had to have a data sharing agreement, be in active practice. And we also have markers to look at to make sure the family physicians are using the EMR regularly for their clinical care, because you can't always assume that. So what we did was we needed labels. I'm not a computer scientist, but I've learned a little bit over the year working with Mahmoud. And basically what we did was we linked the entire cohort of EMRPC patients to our physician claim database in 2015 to identify full consultation visits. There's a specific code for full consultation visits, and they require a referral. They also have a specialist type with that consultation visit, which acted as the label for the machine learning. We then trained on a group of EMR patients who had 1 referral and 1 consultation in that year, which is about 6,182 patients. We did require that there was at least 300 notes that were generated in this manner. So the final predictive model was actually an ensemble of 5 machine learning models, which were the support vector machine, logistic regression, shallow neural network, XGBoost, and convolutional neural network. The referral notes were all pre-processed, so all texts were converted into lowercase, and any non-alphanumeric characters were removed, like punctuation and numbers. For the first 4 classifiers, the free text notes were represented as vectors using the term frequency inverse document frequency algorithm, which is a statistic that reflects not only how frequently a word appears in a note, but also takes into account how often words occur across all other notes to adjust for words that, that occur frequently in all the documents. There was consideration of sequences of 1 to 2 tokens or n-grams when building the vocabulary, and we made sure that the n-grams occurred at least 3 times. For the CNN, each note was represented by a 300 by 200 matrix. So word embeddings of the size of 300 were created to represent words and the words around those words. Word embeddings are actually algorithms that leverage the context of words such as and their surrounding words to create an informative numeric vector for each word. So let's see. Each of the 5 individual models were then trained using a 5-fold stratified cross-validation scheme. The ensemble model had made predictions by averaging the probabilities across probabilities assigned to each class, which would be the subspecialty type, and selecting the prediction as a class with the highest average predicted probability. To increase the precision, or our PPV, we classified all notes with a predictive probability of less than 0.5 as being other. We then deployed these machine learning algorithms on all the EMRPC patients, including those who had multiple referral notes. And then for each patient, we paired 1 EMR referral note with a specialist physician type. And then for people who had multiple referrals, it happens not infrequently, we chose the specialist referral date that was the closest. So in our results, we had 138,920 patients who had a EMR referral notation and 88,204 patients who had a full consultation claim. Amongst them, 28,567 patients had both an EMR notation and a specialist consultation visits. And there were 49,577 unique patient to specialty pairings. So this is not a very nice table, kind of goes with the talk, I think, but it's basically describing the performance of the different ensemble models for the different specialties like cardiology, dermatology, and endocrinology. And we chose 2 different thresholds. So there was a threshold of prediction of 0.5 that was intentionally chosen to increase the positive predictive value to 0.85. And we thought we'd use this to sort of try to reduce false positives. It did come at a cost of recolor sensitivity and performance, but we wanted to be a bit selective to make sure we had more robust measures of wait times. And then we looked at also measures where there was no threshold.
Liisa, about 1 minute left.
Okay, so these are the wait times that we had. So basically, the wait times using 0.5 threshold were slightly shorter than where there was no threshold, but the order was the same. And we see kind of differences where surgical specialties have shorter median wait times than the medical ones. And this was our comparison to our analysis in 2008. And basically we saw that the wait times in 2015 were actually now longer than they were in 2008. But a cautionary note, 2015 is using machine learning and 2008 was using, as Mahmoud would say, we use real people to do abstractions. So overall, we found an increase in wait times when compared to 2008. Machine learning can be used on unstructured EMR data with a fair degree of accuracy, which can allow for more timely results at a lower cost and a larger scale. And this information will be important for decision makers and planners when we're trying to figure out which patients or practices are experiencing long wait times. But as usual, there are limitations. Our training set was relatively small and that limits the performance. We do not have labels for all the free text notes, and that also limits things. And we do have class imbalances. For example, more referrals to dermatology than endocrinology. And the content of referral notes varies greatly, sometimes between family doctors and practices. And also the use of custom forms or tick boxes, they're not words, so that also limits the performance. And we made it.
Thank you very much. Thank you, Liisa, for persisting and for all of the speakers for keeping to time. It's really, really interesting, very different, but very interesting presentations. Now, make sure you keep adding to the questions in the Q&A sort of box, and I'll get to some of these now. I think the first two are comments on Mahmoud's presentation. First, that it's definitely worth watching the video from the last conference in Banff. So I think if that's publicly available, Mahmoud, you may have a few people looking that up online after this session ends. Also that it's slower to fly west because the rotation of the Earth causes high altitude jet streams. So that's very useful to know as well. But look, I'll follow up with a question from Jessia Berry, which is more of a technical question for Branson around the application of the analysis itself. And that's a question around how does the natural language processing correct negative results? So if there's text saying that the result is negative for a virus or influenza, how does NLP differentiate between the negative and the positive responses?
Great, thank you for your question. I do have to give a disclaimer, like I am not a data scientist. Most of the NLP work was done by Elham, part of our team. But I don't think, like right now we're still working on kind of putting all of those extracted entities and really getting the usable result by researchers into a research-ready form, as we like to call it. But with the in-house algorithm, the one that that I developed without using really the NLP models, I have like a lot of different rules that kind of group like negative terms and positive terms together. Like a negative term would kind of override the positive one. So we see things often that are like not detected, not isolated, things like that. So I had my own rules for it, but in the NLP context, we're still working out getting the final results for that. But thank you for your question.
Okay, great. And I think another follow-up question for you, Branson, which was around who does your annotation? And is there potential to crowdsource this very labor-intensive work?
I guess there is a possibility for that. We would definitely have to make sure everything is properly de-identified, possibly using the ICS mask. But current, at least for our project, it was, I did some of the annotations with the help of Hannah Chung, an epidemiologist, and also we often reviewed it with a bunch of clinical content experts, one of them being Jeffrey Kwong, who does a lot of respiratory virus research at ICES. And we also involved some other scientists in the Toronto area as well. So with that, I mean, we didn't go through every single record. So a lot of it was, you know, picking up cases and fixing the in-house algorithm that we created without the NLP models. And I showed in one of the slides that like the number of unique strings after all the cleaning and everything was around, I think, like 50,000 unique terms. Some of them, you know, had names or phone numbers, things like that. But there were like quite a large variety of strings, as it is a free text field, and different labs report results differently. So we kind of, we definitely reviewed all of the like high frequency ones. We did sort it by frequency. So yeah, that was the main group of people. And we went through like as many as, I think at least, I'd say like a few thousand unique records.
All right, great. Thank you. The next question is from Lachlan Daly, and this is for Derrick. And he's wondering whether you've had a chance to investigate the impact of including MI diagnoses from additional diagnoses or procedure codes that are specific for AMI in your algorithm, or whether you've just been looking at primary diagnosis for MI.
I've only been looking at primary diagnosis for MI. It's the MI we actually have three subgroups. It's STEMI, ST elevation MI, non-ST elevation MI, and unspecified MI. So we classify those ways because admissions for non-STEMIs, they less likely get transferred. The clinical guidelines say they can be managed later. If it's not severe, they can be managed later. Whereas if it's an ST elevation, the guidelines say they have to be transferred immediately. So that, and also a lot of the unspecified MIs probably the ones where the patient died early and there was no chance, they couldn't diagnose the MI. And so you wouldn't expect a transfer there. With regards to the procedures, we did look at procedures, whether they had an angiogram only, or they had an angiogram and a stent put in, or whether they had a coronary artery bypass surgery done. So we did look at those variables. So if you get those procedures done, you're much less likely to get transferred out because it's already been done.
So then you found that was there a difference in performance of the machine learning algorithms based on whether you had a primary or additional diagnosis or a procedure or a diagnosis?
We couldn't tell if the methods is because it's just a random selection of variables that go in every time. So it's sort of like a black box where it gives you the outcome. So probably something like feature learning that those ones which tells you which of the variables are predictive. So that's probably one of the next steps if you can predict. So it's a bit like logistic regression, but it's on at a different level.
All right, thank you. Look, the next question for Liisa, and this is from James Rafferty saying, interesting choice of machine learning models. Why did you choose a shallow neural network in particular?
Well, you asked the wrong person on that one. Don't know. My honest client, you know, that's part of Mohammed's thesis, and I think he's trying to test out different learning models and how they work with this sort of data. And yeah, so you'll have to defer to Mohammed on that one. Sorry.
I guess I had a similar question, a related note to Mahmoud, which I know in the mask you had the choice of a variety of different parameters, including the choice of which model you wanted to use, whether it was the Elmo or Glove or whatnot. Was there a difference in performance of the different models and their ability to do the masking? And what would you recommend if people here are, for example, exploring similar different types of methods, being neural networks or otherwise? What do you find as the preferred approach, or pros and cons of each?
Sure. I should also provide a disclaimer that I'm not a data scientist, and so I was not a developer. I was the one that bringing in all of these data scientists together and bringing the problem to make it a real world problem and solve it. But I I can mention based on what I learned that the 3 different models are performing differently, but they requires different resources. So for example, one which I'm not sure which one of the 3 models was, it requires GPUs for analysis. So it depends on what are available to you as an end users and what type of resources that you have, then you have different choices. And some of the models work for some of the entities better than the others. So for example, we need to mask names, and also we need to mask addresses and phone numbers. So these are, you know, each might work better for one and not as good as the other one, or depends on the resources that you have. So these 3 were the ones that we realized that these are probably the best options that we can provide to the end users.
Mm. And so with the end users, in terms of, I guess, the next step of using that data or releasing that data, would there still be a degree of manual or clerical review of the information that comes out of that to ensure that de-identification has occurred?
Well, I guess that would depend on the organization and the you know, regulations and policies that are applied on the organization that is using this. So I would assume for some organization it would require some sort of manual review at the end, or it could be just manual review at certain time, just to make sure that some sort of auditing in general, like once a year, just checking on and making sure that the model is still working. Of course, the medical data keep changing in terms of the you know, the narratives and the scenarios that you could see, and also it varies from one jurisdiction to another jurisdictions, or different, you know, acronyms that different physicians use in their notes, and some might actually overlaps with some of the names and confuse the models. So for that reason, for sure, we would recommend to audit the application once a while, and making sure that it's trained based on the most recent data that is available to that jurisdictions. But of course, some degrees of annotation will happen at the beginning in order to make sure we are providing enough annotated, you know, manual reviewed records to the model in order to train the model.
Okay, great, thank you. A comment from Maren Smith, excellent presentations, thanks. Derrick, are there implications for national statistics from your work, particularly in the trend of transfers over time?
Yes, there is. That was the reason for this study. We were working with one of the statistical agencies, won't mention names, and they were interested to get counts based on transfers, and we all know that there's an overcount. So that was the impetus for this study. So once this is done, we probably work together with them to generate more accurate counts of the MI events. And it could also be applied to other areas.
I suppose I have a follow-up question where I think it's amazing the capacity to use these kind of models to predict information that we're missing in administrative data in particular. But I also acknowledge there's always a sort of margin of error that's associated with, you know, this information that we're inferring and deriving. And I guess this could be a question for multiple people, and maybe Liisa and Derrick. To what extent do you think the margin of error will be acceptable in, say, reporting national trends in admissions for AMI, or around the proportion of patients who've had a referral? Have you found it difficult explaining the nuance of that margin of error coming from these predictive models to the end users of this information?
Well, I think at this stage, we're dealing with the situation of no information. I mean, we really, we just have no information in which to trend anything. It's definitely not perfect, but this is not a situation where we're providing therapies or treatments to people. It's trying to look at regional differences for wait times. So I think at this stage, it's better than nothing. I think what needs to happen is trending it over time and seeing if it's picking up changes, and you know, continuing to work with new data and refining the methods to make it more accurate. But I think at this stage, I think it's more than good enough.
Yep, agree.
All right. And I think there's a question on a slightly related issue around the perception and support of the public and the end user about, you know, the sort of use in AI and machine learning in interrogating data. And that was a topic of one of the sessions yesterday, where I think there was a really, well, there was a good discussion. So another comment saying, thanks for the amazing presentations. From the data subject's point of view, are they generally supportive of these kind of initiatives? And I guess particularly when you may be dealing with unstructured data that contains potentially sensitive information such as names and addresses, what are the types of privacy related barriers you might have come up against, and how have you navigated this space? I guess that's probably more for Liisa, Mahmoud, and Branson.
Well, I'll start it off, but I think a couple things. I think working in an environment where it's clearly stated how the data is kept private, who accesses it, who access the data, what it's used for, I think is very helpful. I know amongst the medical profession, I deal with I'm a family doctor and I work with family doctors. And I think, again, they are working in a void of information about the type of care they provide. And the best you can get to 2020 data, they're very excited about, but they do want to know things are private. And I think working in a place like ICS for, I don't know, what's the 40, 35 years, it's been so clearly documented and vetted on how privacy for both patients and for providers is secured, that I think that kind of, there's a trust with the medical profession towards an institute like ICS. So I think that's one aspect.
And I can pick up from there. I agree with Liisa, you know, the mask application that I talked about was actually for providing that reassurance that we are properly respecting the privacy of the data. There are, of course, some challenges, you know, technological challenges further. We're working, for example, for multimedia data, images that have names embedded on it, or PDFs. So these are more difficult than the identifying free text fields. So yeah, there are more challenges to tackle, of course, but definitely one of the reasons that we are looking into applications like mask is to address these issues.
Oh, fantastic, thank you. And I guess I have another question around the quality of the data. So I know from my experience working things like GP, such as family practice data, the level of information recording varies greatly between GP practices and practitioner. And I imagine there's a lot of variation in, say, the way that lab reports are recorded as well. To what extent do you think variation in how the unstructured data is captured and recorded sort of impacts on the potential end user of this data?
Well, I'm just going to say it does. I think that's why performance isn't as good as the work from Australia. I thought that was those are nice numbers. But I think, you know, there's a big movement. When we started working with EMR data 10, 15 years ago, there was a movement that you have to get everybody to code the data. And it was very much family physicians should know how to code data. It's very important for quality improvement and research. And I can tell you, I'm a family physician, we're too busy. You know, we are trying to do patient care. It's coming at all angles. And I really think with machine learning and other sort of advanced analytics, I think we can figure out how to work with the messy data. It's about, okay, this is the reality. How can we work with what is and have providers do what they need to do and us get better at codifying the data.
Thank you, Liisa. Now I'm just going to have to quickly wrap up. I think we have less than a minute to go. So I'll just reiterate, there was another comment saying that all the talks in this sessions were great examples of machine learning to improve data quality, usability, and to derive new information from unstructured data. I completely agree, and I think everyone who's watched this session will agree, and thank you all for the quality presentations that you've given. The recording of this session will be available on the conference platform within 48 hours time, so be sure to check it out if you want to rewatch. And if you enjoyed this session,